Hello everybody and welcome to the final topic for statistics called the normal distribution. Now this normal distribution is actually used very commonly in our everyday lives. Some of you may have heard of this thing called a bell curve. This over here is the bell curve. This is your probability distribution function or PDF of your normal distribution. Now this curve works on two parameters. Mu, which is your mean, and sigma square. Sigma square is your variance and sigma is just your standard deviation. So when you want to say a variable x is normally distributed, we have x and then tilde and mu comma sigma square. Remember when we write this in here, it's the variance. But when we're doing calculations, it's usually using the standard deviation. Now what is the normal distribution curve used for? Something like IQ, which has a mean of 100, and if you're above average, you have an above 100 IQ, and if you're below average, you have an IQ of below 100. So IQ is something that is normally distributed. So maybe let's say you have an IQ of 150, and that's over here. And you can see that the probability of you getting an IQ of 150 and above is actually quite low. By the way, this curve extends infinitely outwards, left and right. So you can see that this area over here is actually really low. If you want to find the probability of a variable x landing in the range of A to B, so looking something like this, what we are doing is just finding this area over here. What we can do is just take norm CDF, A, B, and then mu sigma. Note that this is sigma, the standard deviation, and not the variance. So this over here is to find a probability between a certain range. Now for the next one, we want to find A such that the probability that x is less than or equals to A equals to k. What this is trying to say is that if we're given this area coming in from the left, we know as k, we can figure out the value of A on the x-axis. So if we take the inverse norm of k, and then we add our parameters mu and sigma, this will give us our value of A. So if we are given the probability and we want to find this value A on the x-axis, then we have to use inverse norm. Now similar to binomial distribution, we'll be doing some very important questions. The IQ of the general public, represented by the variable x, has a mean of 100 and a standard deviation 20. For part A, find the probability that the mod of x minus 80 is greater than or equals to 30. So what I want to first do is solve this inequality. This means x minus 80 is more than or equals to 30, or negative x minus 80 is more than or equals to 30. So if we resolve this inequality, this becomes x is more than or equals to 110, or x is less than or equals to 50. So again, we're trying to find the probability that this variable x has this condition. And this condition is equivalent to x is more than or equals to 110 and x is less than or equals to 50. So this over here is represented by these two green areas over here. Now what I can do to find this total green area, which is just your probability, is actually take 1 minus your blue area. If you look at this, 1, which is your total probability, is the total area under this normal distribution curve. So taking 1 minus the blue area will give us the green area. So we take 1 minus, and the blue area is just a probability. We're trying to find the probability that x lies between 50 and 110. So we have norm CDF 50, 110. That's our range. And then mu sigma. Mu is your mean and sigma is your standard deviation. And if we input this into the GDC, we'll get 0.315. Now for norm CDF, I'm just going to key in norm CDF. And then we have 50, 110, 120. And we want to find 1 minus this norm CDF. So we press enter and we get 0.315. Now the next one, find D if the probability that mod x minus 100 is more than or equals to d is 0.125. So from the get-go, we know that we'll be using inverse norm. Why is this so? We are given the probability and we're trying to find d over here. Let's solve this inequality. We should get x is more than or equals to 100 plus d, or x is less than or equals to 100 minus d. So this can be displayed over here. And if you look at this, the graph is actually symmetrical. So these two blue areas actually are the same. And we already know that this probability, that x is more than or equals to 100 plus d, and x is less than or equals to 100 minus d, the total probability over here is equals to 0.125. And since both these areas are the same, I can just do 0.125 divided by 2, which is equals to 0.0625. That's the area under the curve here, in just one of these blue areas. By the way, one thing that I forgot to note is that inverse norm takes the area from the left. And the reason why this is so is because it's coded to take the probability that the variable x is less than or equals to a certain number. So in this case, if we take this certain number to be 100 minus d, this will be equal to 0.0625. And as such, we cannot use inverse norm for something like this, because this is x is more than or equals to 100 plus d. The area must come from the left side. So we have inverse norm of the area, comma, mu, which is the mean 100, and then sigma, which is the standard deviation 20, will just be 69.318. For inverse norm, I'm just going to write inverse norm. We have 0.0625, comma, 100, comma, 20. Press enter. Now we know that this is equals to 100 minus d. We're trying to find when px less than or equals to 100 minus d, right? Then we'll get this area, 0.0625. So we know that 100 minus d will be equals to 69.318, which means that d is 30.7. Now the last part for C is a bit more difficult. Of the people in the general public, only those with an IQ of greater than 130 are admitted into the Mensa Society. Find the median IQ of the members of the Mensa Society. So let me draw my curve over here. The mean is 100. But what I want is an IQ greater than 130, which is somewhere here. So what they want is the median IQ of the members of the Mensa Society. Mensa Society means you're somewhere in this blue area. And if you remember, the median will split the area into two halves. Since we're looking only at the Mensa Society, which is where this blue area is, the median IQ will split this blue area into half, because we want the median IQ of the members of the Mensa Society. So let me use this red line over here. This is your median IQ, but for your Mensa Society. This over here will be half of the total blue area, and this over here will be half of your total blue area. So how do we want to do this? We first want to find out what is the total blue area, right? Your total blue area, you're trying to find the probability, so we're going to use norm CDF. For the blue area, the lower bound is 130. So we have 130. And then your upper bound is actually positive infinity. It goes all the way infinitely. In GDC notation, we'll write this as 9E99. And then we'll have our mean and standard deviation. We should get 0.066807. So that's your blue area over here, from 130 to positive infinity. To find the median IQ of the Mensa Society, we have to use inverse norm. So we need to know the probability that the variable x is below this median IQ of the Mensa Society, which I will call m. So in this case, we want to find out this probability of this entire area over here, which is just this blue area, and this area is just this, but divided by 2, and then we want to plus this red area over here. That area is actually just 1 minus the total blue area, because 1 minus the total blue area will give you your red area. We'll get 0.9665. Finally, what we want to do is inverse norm of 0.9665. We're given the probability or the area under the curve, and we want to find the value of x. or in this case, just the median IQ of the Mensa society. And we should get 137 3SF. So what this is saying is that half the people in the Mensa society have an IQ between 130 and 137, and the other half have an IQ of greater than 137. Now the final thing we're going to look at is the standard normal distribution. Why is this useful? Now a standard normal random variable z has a mean of 0 and standard deviation equals to 1. To transform your variable x, any variable x that is normally distributed with a mean of mu and variance of sigma square into the standard normal distribution, what we can do is take z equals to x minus mu over sigma. This is actually in your formula booklet. Now the reason for standardization is to use it whenever we have an unknown parameter. So if we want to find a parameter of mu and or sigma. Let's try this out and listen closely. The mass of cans are normally distributed with a mean m. So we have an unknown parameter. We don't know what our mean is. And standard deviation 0.5 grams. The operator wants to set the mean such that not more than 2 cans in 1000 on average are less than 300 grams. Find the minimum possible value of m to achieve this. So let's first draw our graph. Our normal distribution looks something like this, with a mean of m. Now we want to set the mean such that not more than 2 cans in 1000 are less than 300 grams. So we have 300 over here, and this area is 2 out of 1000. So what I can say is Px is less than or equals to 300 is equals to 2 over 1000. Okay, if I want to standardize this, I'll change this x to a z over here by taking 300 minus mu over sigma. So we have 300 minus the mean over sigma. In this case, sigma is the standard deviation 0.5, which is still equals to 2 over 1000. I want you to note, after doing this, we still have the same number over here. And does this form look somewhat familiar? We can actually use inverse norm on this. We have our probability or area over here, and we want to find out what's inside here. So what we'll be doing is inverse norm of our probability, and then remember we have mu and sigma. So remember our mean for a standard normal distribution is 0, and our standard deviation is 1. This is actually equals to 300 minus m over 0.5. That's what you're trying to equate to. And if we put this inverse norm into the GDC, we should get negative 2.878. Now if I want to solve for m, this is very easy. I'll just get m is 301 grams. Here's the summary sheet for normal distribution. Thank you so much for watching.